My name is Christopher Meiklejohn. I'm a PhD student, or PhD candidate, I guess now, at Carnegie Mellon University. I'm going to talk a little bit about what I've been working on as part of my thesis. It's kind of cool to be back here because the last time I talked here was before I started my PhD, 3 months. So I don't know what that means, but hopefully I have something cool to talk about today. More specifically today, I'm going to talk about microservices. So many of you are probably familiar with microservices. For those that you aren't, a microservice architecture is an architectural style where we construct applications by composing a bunch of services together. These services communicate over the network using remote procedure call, and then we develop, deploy, scale, operate, and manage these services independently. So 3 examples that you probably are familiar with are first Netflix, which in 2021 was composed over 1,000 services. Uber, which in 2022 in 2016 had 2,200 services, where 120 of those were involved in the process of getting somebody a ride. So kind of connecting our drivers with our riders. And then finally, DoorDash is composed of 500 services in 2022, where 100 of these are involved in the core flow of getting Dashers connected with merchants and the consumers that they service. So as of 2021, all 50 companies in the Fortune 50 were talking about microservices. So microservices are everywhere, regardless of if you're working on them or not. And I personally believe that microservices represent the most common, in terms of what developers are writing today, and complex type of distributed application today. And I just want to present 2 kind of data points here. One is that Twitter, for instance, back in 2017 operated this massively large 10,000 node Hadoop cluster, and everybody was very impressed at the size of this cluster. But what we want to consider here is that most of the software running here was one version of Hadoop running on a lot of nodes that implemented 1 or 2 distributed protocols. Now, if I put this in contrast with microservices, for instance, at DoorDash, we have 500 different microservices, and each of these services provides a different API. It's got different functionality, and it's deployed at a different cadence, so that could be up to multiple times a day. So at any point in time, reasoning about the correctness of this application or what this application will even do is tremendously complex. So what does a microservice application look like? This is Netflix on my iPhone here, loaded on my iPhone. Each of these sections of Netflix's homepage, as an example, are provided by a different service. So we see here in the top row, we might have the My List service provide some content for their My List, which are the things that I want to watch when I eventually have free time as a PhD student. And then in my bookmarks row, I have the one thing that I started watching, where I got about 3.5 minutes into the first episode of Seinfeld. But this is the things that I want to watch. And then finally, my user recommendations row says, well, I watched 3 minutes of Seinfeld. I probably like witty sitcoms. And so here are some sitcoms I want to see. And so what we can notice here are that each of these services are developed by teams that are composed of different sizes in terms of the amount of developers. These developers have different skill levels. And then once we deploy these applications to production, we scale them by using different numbers of servers. Now, in terms of composing and composition to build services, what I do is I have one team or many teams that are responsible for taking a dependency on the services that they need. So here, the gateway will take a dependency on these 3 different teams and these services to construct my Netflix homepage. So why do we build applications like this? So the reason we build applications like this is that microservices solve for a very particular socio-technical problem. They want to solve the problem of rapid delivery of software at scale in terms of features as the organization grows. And so the way we solve this problem is that we apply a social solution, which is to minimize coordination within the organization. We want to break our development out into different teams. We want to size those teams accordingly, and then we modularize our feature development this way. Now, this modularization into components where different components communicate with other components to deliver functionality implies that our technical solution means that we're all now building distributed systems. These are not the easiest types of applications to build, especially if you've seen the many talks here at Strangeloop about how hard distributed systems are. Now, when we move to this world where we start building distributed systems, the first thing that we kind of have to accept as a change in our reality is around code quality and the typical tools that we use to ensure that code is developed at high quality. And when I talk about each of these things, I want you to consider, even if you were developing a system like Cassandra, So even if you were building a distributed system like Cassandra, you would typically be operating in one repo, working on one protocol, and it'd be written in one language. The difference in microservices are, first, that we have integration and functional tests that are harder to write because we have to start talking to dependencies that might be only available in AWS or only available in a Docker container, or I may have to write expensive mocks to do this. So this makes integration and functional testing more challenging. The second is that academics everywhere have spent a lot of time building wonderful static and dynamic analysis tools for ensuring high code quality, and we kind of throw this away when we move to this multiple language, multiple repo model where static analysis, which is already hard in general, becomes much more difficult. Dynamic analysis becomes harder. And now we need to actually start reasoning about when an RPC server makes a call, when RPC client makes a call, what RPC server is that talking to? And then finally, we're stuck using our traditional IDEs. No one's really envisioned what an IDE would look like if we wanted to focus on what microservice development or daily microservice development looks like. And so we don't really know what this will look like. And finally here, just to highlight, this is an area that I've been thinking about for a while. In 2019, I wrote this mock-up for a fellowship that I was applying to try to get money to say, I think this is a great problem. I didn't get the money, but I kept working on the problem. And that's why we're here today. So when it comes to distributed systems, code quality is also an issue. But we also have all of these fundamental challenges of distributed systems, right? Distributed systems aren't easy. And so what microservices say is, well, we're going to set up a set of design tenets to make distributed system programming easier. So what do we mean by that? So the first is that when you're building microservices, you're not explicitly managing shared state. No one's implementing Paxos as part of their microservice application. Nobody's writing a database. What we're doing is we're relying on cloud storage and other systems that have solved that very hard problem of distributed state management, and we just take dependencies on those systems from our application. This eliminates one fundamentally hard problem. The second is that we typically try to avoid reasoning about distributed versions. And so we think only in terms of forwards compatibility. We use protocols that transparently support backwards compatibility, such as gRPC. And we think about using feature flags to control when new fields are written. And we roll our software out incrementally in that way. Another thing here is that we don't even think about the reliability of the messaging protocol. We just say, well, gRPC will get the message there. Right? We're not concerned about message omissions when we're using gRPC. And then finally, the last bit is we don't even think about crash failures. So the bane of every grad student working on a new version of Paxos' existence, servers crashing. We don't even think of these. What we say is that we'll run Kubernetes. We'll use a health check. When things start failing, we'll restart it. We'll throw a replica set in there. We'll have multiple machines. We'll load balance across those machines. And when something fails, we'll probably hit a non-failed replica if we make a request again. And eventually, that replica will be ejected out of the pool. So the idea here is that these things make the challenges of fault tolerance transparent, right? And the last speaker was thankful enough to kind of set me up perfectly with the ball right there in the air in saying that, no, it's kind of about this end-to-end argument, right? Application bugs are not going to be handled regardless of how much fault tolerance we put in the messaging protocol or in the server itself. And so what do we mean by that? We mean that engineers have to consider that nodes may occasionally return errors. Now, even though our health check will remove those nodes, our application's still going to see it once, presumably before the health check disables it. We also have to deal with the reality that bad code gets shipped. As much as we want to say this doesn't happen, it happens. Somebody will deploy something, it's going to return a null pointer exception or array out of bounds or whatever. It's going to cause a 500 internal server error. And these things happen. And no health check is going to save your application from observing these. These also get complicated when errors only occur under certain arguments that are supplied. So you could have services that just fail when given a particular argument, like somebody's allowed to give the system an empty list or something like this, resulting in null pointers or array out of bounds or whatnot. And then finally, we end up with problems with transitive dependencies maybe malfunctioning in terms of timeouts or other user or application-specific ways. And so we have to deal with this in the application. So what do I mean by fault tolerance? So in this example, we'll consider the case where the bookmark service happens to be down. So the developers first have to answer what should happen when the bookmark service is down. What should I do? What should the application do? Should it return an error? Should it not? And then, once we know what should happen, we then have to verify that that's what actually happens. So in terms of knowing what should happen, you might be familiar with this. We apply these kind of microservice fault tolerance techniques. So what do they look like? So one example is using something called a fallback. Basically, every talk on chaos engineering you've ever seen talks about this, where you say, well, that bookmarks content was unavailable, so let's load some content and display some other information, and hopefully that doesn't degrade the user experience as bad as we thought, as bad as it could. But there are other types of fault tolerance techniques, such as retries. We might retry a request, simply hoping to hit a non-failed replica. We might have timeouts to prevent ourselves from waiting too long because we don't want the user's experience to be really bad. We'd rather show them something rather than waiting a really long time to ask them to try again. And we might use more advanced techniques such as load shedding or circuit breakers, where we try to remove load at the source or destination to keep the system online and be more tolerant to faults that can occur. So that's the what should. But the question now is what actually happens? So in terms of answering what actually happens, what developers typically do today is they rely on a technique or a suite of techniques that's called chaos engineering. You might be familiar with this with Chaos Monkey or similar systems, where you apply randomized fault injection at a coarse or low level and try to identify systems issues. Now, we saw a lot of companies using this. In fact, we did a gray literature qualitative study here, and we saw that, out of these 52 places where people talked about finding bugs, 32 of them were using chaos engineering, and it works great. But chaos engineering has some negatives, right? So chaos engineering, first, it's low-level, coarse-grained fault injection. I'm going to turn off machines. I'm going to shut networks down. I'm going to do stuff like this. This is a rather expensive way to try to find application bugs that might be just throwing an exception. It's also difficult to trigger certain bugs. So if I trigger that bug, how do I even know if the request I issued from the outside of the system was even affected by that fault I injected? A second problem is it's probabilistic. I don't know if I have, without precise targeting, I might be injecting faults not knowing who's observing the failures or if anybody's observing them at all. And when I find a really interesting bug and I say to my colleague, check this out, I might not even be able to reproduce it without requiring specific control of the system to allow me to sequence the messages just right to surface that bug. It's expensive. If you want to do this in staging and your staging mirrors production, it's expensive. If you want to do it in production with a copy of your traffic, it's even more expensive. And then finally, it has potential customer impact, right? So Netflix might say, well, it doesn't matter if we do this because most of the time the Netflix homepage will be fine, but maybe some things might be slightly different. It becomes a lot more expensive for you if you're a company like Amazon or Target or Grubhub or something like this, where you risk the fact that when you go to inject a bug someday to figure out if your system has resilience issues, you might prevent a user from being able to purchase at that moment. This is despite me showing you on the screen that HSBC uses it, so I don't know what that says, but we'll allow the audience to make their own conclusions. Where is chaos engineering really good? Chaos engineering is really good with end-to-end incident response, right? I've already found most of my application bugs. I want to see what happens when a fault occurs, and I want to see, does my engineer get paged with pager duty? Does the system, does some auto-scaling rule trigger, something like this? So it's good for this kind of end-to-end incident response. So how can we do better? So what I focused my PhD on is what I'm referring to as development-first resilience tools. The idea here is that we want to integrate kind of a vertical integration of fault injection throughout the entire development and deployment process. And I want to do this building on what developers are actually doing. I don't want developers to write specifications. I want to build this up from the tools, the things they're already doing, the tools they're already using. And so I see this as kind of sitting between these two areas, kind of the more academic area of formal methods, specify it all and verify my specification and then make sure my implementation refines that. And then chaos engineering, which is what most companies are doing, which is let's get that code out there, let's start injecting faults and see if the system is resilient to those faults that occur. So I'm going to start by talking about these bugs, these partial failure bugs. So I'm going to give you two small kind of motivating examples to get you for a feel of what kind of things can be the start of an incident and how developers deal with them. And to do that, I'm going to have a small ride-sharing service that's composed of 5 services. So my API gateway talks to 3 services. My payment service talks to a service. Let's call it Stripe. Doesn't matter what it is. But it's a third-party payments processor. I'm going to assume that I wrote end-to-end functional tests that exercise this entire application when no faults are present. And I'll say that all of these things, as simple as they are, we abstracted these from real incidents that caused companies real pain and loss of revenue. So for incident 1, the workload service C is deployed with a bug. And this activates a failure at service A because service A doesn't anticipate that it will get this bad response back from C. So this is a fairly standard example of bugs where the developers of service A just didn't anticipate the failure of service C, and they didn't have associated error handling. And so what the developers would typically do in this scenario is they would write the necessary error handling code, hopefully test it using a mock, maybe not, maybe in staging, and then deploy this to production. So this is one very simple example of where developers don't write error handling code, and maybe it's just because they just don't think about it in development, or sometimes, as previous academic studies have seen, they just write / to do, and they try to come back to it later, but may forget. A second example is a third-party dependency failure. So here, Stripe begins returning errors. Now, this is to be expected. Stripe doesn't provide you with 100% availability guarantee. They provide you with something reasonable, like 5 nines or something like this. And so the developers at service B, the payment service, don't have error handling for this transient condition. But what they do decide is rather than just put an error handler in place to return a message to the user, they'll say, well, if we can't pay the user for the work they're about to do when they're driving for us tonight, if we can't pay them now, we always can reconcile that payment later. So let's say if Stripe's down, let's write some data, do a durable queue, maybe Kafka, and then we'll reconcile those payments later and we'll return a successful response back to the user anyway. So to identify these two classes of bugs, we need to first solve for the missing test oracle, right? And what do I mean by this? So first is engineers must eventually figure out all of the possible ways that the remote calls can fail, so enumerate those possible failures. And then to guarantee resilience, they would have to manually check all possible permutations of those failures. So the key observation here is that developers are writing functional tests that capture end-to-end behavior when failures are not present. So can we automatically synthesize the variants where the failures are present and then force the developers to update their code accordingly? So the technique that we invented to do this is called service-level fault injection testing. We start with an end-to-end functional test that asserts the behavior when no failure is present. So here we issue a request and we get a 200 OK response back. We then record all the remote communication that happens, all these green edges. And then we re-execute the test with all the possible fault permutations, looking for assertion failures. Now, there will inevitably be assertion failures because the developers have never specified what the behavior of the application when a failure occurs is. So the developers will have to update that. Now, when we do this search, we can explore this in two possible ways. So one is we can observe the communication protocols that are used between different services and automatically inject all possible exceptions for those communication protocols. Or we can be a little bit smarter and try to rule out classes of failures using a static or lexical analysis that looks for error codes that are never returned to the user. But the key here is that automation needs to happen because while I've shown you this very, very simple microservice graph, I told you at the beginning that there are hundreds of services involved, right? So if you're dealing with a system where 100 servers are involved in making, getting a ride or making a purchase, then simply kind of enumerating this manually is not possible. Now, the process of updating the test looks roughly like this. We start with a test here that executes the path for the user C Meiklejohn and asserts that we got a 200 response back. And then when we inject our first fault, we get an assertion failure because the system returns an error back when the asset service is down. And so at this point, the developer is prompted, do you want to return an error under this condition? Is that the correct way that this fault should be handled? And if so, then the developer says, well, we can't do anything if our assets are offline. Then what the developer would do is say, add some code that say, if a fault was injected, I expect the response to be 503. But when we get to our example where the payment service is down, we get another assertion failure because the payment service, the response should be 200, but we should have additional data written to that queue. And so here we say, well, if a fault was injected on that payment service, then I expect the response to be 200, not 503. And now this process is repeated until all of the scenarios are covered. And it looks like you would have to write conditionals for every scenario. In practice, it ends up not being really that many because many failures are treated the same. Now, we're using functional tests. And what that means is that when you're testing with functional tests, they exercise hundreds of services, which means that if we're going to explore all of the possible permutations of those failures, there are quite a large number of them. So why do we test all of the possible permutations of failure? So we'll start with this simple kind of abstract view of the previous graph I showed you. And we'll assume that each service can only return one error. And that error will be a 503 service unavailable. That's the only thing we're going to test for. So the first thing that we need to do is we need to test each service's resilience to a direct dependency returning that error. So we start by injecting a failure at E to test whether B has error handling for that failure. And then we have to test a failure in B, a failure in C, and a failure in D in 3 different test executions to make sure that service A has failures as error handlers accordingly against those 3 possible failures. The next thing that we have to do is, because we're not using a static analysis or some sort of smarter dynamic analysis, we need to test for whether or not the developer has written a conditional, for instance, do something special if B and C are down. Now, you have a trade-off here. Either we explore additional tests to suss out these conditions, or we do a more advanced dynamic analysis, like seen with protocols like Dart or other concolic testing protocols. But that doesn't work for microservices where we need to mechanize this across multiple frameworks, multiple languages. So rather, we throw compute at it, and we just say, let's test all of the possible combinations, which is BC, CD, BCD, to make sure that the developer didn't write something that says, well, if B and C failed and D didn't fail, do this really special thing. The question remains, though, do we have to test this combination of D and E failing together? And it turns out that there's a property that we identified here called service encapsulation, which under certain microservice design constraints means that the failure of service E is not directly visible to A in order so that A could write conditional logic based on D and E's failure together. So as long as they're not sharing registers in a database, or they're not directly exposing state in some other way through writing to a file in the file system or something like this, it is impossible for A to basically write conditional logic based on the simultaneous failures of D and E when encapsulation is done properly. So in principle, if we've already seen what A does when B fails, and we've already seen what B does when E fails, and we've already tested all of the possible responses, failure responses that B can exhibit to A, we already know what B will return to A when E fails, and therefore we've already tested the combination of D and E together. Now this property that allows us to do that is called service encapsulation. The actual algorithm is called dynamic reduction. And I don't have a lot of time in this talk to go through the details. There's a paper if you'd love to read it. I would love to send it to you, because that's rare. But with dynamic reduction, it's important because it reduces the exponent from the maximum, from the fan out of all the RPCs issued in the system to the maximum fan out of a single service. So that means if you only have one service that goes 5 wide with a fan out, that's your maximum fan out. You don't have to worry about these applications where you're issuing 100 RPCs to 100 different services. OK, so before I kind of talk about mechanizing this for real, I'll just briefly touch on the academic evaluation. So I will say, for you inspiring academics in the crowd, doing research in this area is extremely difficult. There's no industrial microservice corpuses that really exist, corpora that really exist. The ones that do have been constructed by qualitative researchers to examine properties inherent to microservices, and they're not nearly enough to complain bugs that arise from the choice of a microservice architecture organically. And so when they have synthetic bugs, they're kind of unrealistic. And so what we needed to do before we could even evaluate any of this stuff or publish it was we needed to actually re-implement a bunch of small reproductions of descriptions of bugs that we found on the internet. So in doing that, we were able to find a small bug that Expedia had and reproduce it, and similarly for MailChimp, Audible, and Netflix. And we were able to evaluate these small reproductions written in Python, and with a prototype written on Python, and we were able to identify all of the bugs. and show that that dynamic reduction technique that I talked about gets you, can get you an observed 75% decrease in costs of doing the exhaustive search. Now, I want to highlight two examples here. So the key I told you was about this encapsulation property, which means that you get benefits from going deeper rather than wider. And so what we see in our Netflix example, we go very wide. We issue requests to a number of services, and then they all come back, and we might have written conditionals based on any of the ways that those services can fail. Where in the Audible example, it's constructed deeper, which allows us to kind of avoid some necessary tests where that visibility property comes into play. And so maybe as a general insight, if you want to leverage this encapsulation property, deeper is better than wider. Wider is harder to test because you have to test all those possible permutations if you want full coverage. Okay, so I'll kind of get in the last bit, which is what I've been spending the last year or so on, is how do you make this thing so that people can use it in a nice way and integrate it into their workflow, right? So a tool like this is only really valuable if you get developers using it early and you can build an understanding of application resilience from the ground up. So to do this, there were a number of challenges that I had to address. So the first was, how can we avoid manual modifications to support testing? So every company I talked to when I was shopping this stuff around, they were like, yeah, we're really interested. Oh, you got to modify your programs. No way. Like, they do not want to modify programs for testing. They want it just to be the way they are so it integrates into their existing flows. And so this is important because we needed to instrument the RPC libraries that were being used to inject faults, and also instrument the concurrency libraries that were used so we could propagate the state through that we needed for dynamic reduction. The second challenge we had to address was how do we smoothly integrate this into the workflow of developers so that they could integrate it with existing CI/CD processes and be able to use a debugger and all of this kind of stuff. So to answer these two things, the first was that we tried doing this ourselves, but I am but one developer on an academic project. So what I did was I leveraged OpenTelemetry's existing distributed tracing framework to integrate all of our stuff so that if you were using OTel, you would get all of these benefits for free. This was using interceptors and decorators to support fault injection on any RPCs that were being issued in the system. And second, for propagating that state across threads and futures and coroutines and all these fun concurrency primitives needed for dynamic reduction. The second bit was that I needed to integrate this directly into development and testing workflows, and so I did this in two ways. First, I integrated a version of our tool, which is called Filibuster, into JUnit for local development with this kind of fault injection so that you could use your debugger and IntelliJ and all this nice stuff, so you could test small subgraphs with direct dependencies. And from there, I created a standalone filibuster tool for use in a staging environment that was flexible enough to support whatever testing strategies people were using there. So we'll talk about the OpenTelemetry stuff first. So in terms of automatic instrumentation, the goal was to be able to do this. So for Java applications, we were specifically working with Java and Kotlin. We wanted the ability to provide a Java agent at runtime that would automatically instrument our gRPC calls that were being made, our HTTP calls that were being made, and support fault injection, and also propagate the state we needed to do our algorithmic reduction. Today, we have support for this in Google gRPC, so if you're using any of the standard Google gRPC stuff or anything built on top of that, this works transparently. And we also have some more for the Armiria web programming framework if you're using their HTTP or gRPC client libraries. Now, we also put all of the smarts into a separate library, so writing these libraries that just bridge the gap between where our stuff leaves off and OTel picks up is about 200 to 300 lines. And so we imagine that this could easily be extended to more languages. It's just we haven't really had the opportunity or need to do that yet. So this was the first big step. So now I'll talk about what it looks like to do this in JUnit. So when we wrote the original version of this for Python, it required a lot of manual external tools, but we wanted to really smooth out that process. So here is an example of the world service, the hello service, and kind of a three setup application here. So we have our test, which is JUnit. It's going to talk to the hello service. The hello service is going to talk to world. and then they'll respond. So first, test issues a call to the hello service using the partial hello endpoint. That string is then sent to the world service. The world service just really takes that string and echoes it back with world appended, and then our hello service prepends hello back and returns that to the end user. So here is an untested error handler that I don't have any error handling code. I don't have any specific test written for. I only have my starting test. And what it does is it says that if the communication between hello and world are interrupted and that call returns a status runtime exception of any arbitrary gRPC code, then it will trigger this catch clause at the hello service, which will take that and it will just return that back with a wrapped in a data loss gRPC exception. So this is the code that we want to test. Right? Here's the fault we want to inject. Here's the code we want to test. So to do this, what we do is we take an existing JUnit test, which is just really left off the slides because it's really 3 lines of boilerplate, basically. What we do is we take this test and we change the annotation to filibuster test. This will automatically take that test and extend it with 2 variations where we inject timeout exceptions and we inject unavailability exceptions, which is the gRPC equivalent of a 500 internal server error. This will cause 2 additional tests to get synthesized, which will be shown as failing tests in your editor immediately. And we see it does exactly as we expected. We injected a deadline exceeded, and we got it wrapped in the data loss exception, and the same for the second bug. Now we can customize this further. Filibuster has an analysis file that can look at code and try to figure out what exceptions to inject, which I talked about earlier. That is optionally can be supplied here using our annotation. Or you can use programmatically, you can build a custom set of errors that you want to inject. And so today, what we've done, we've tested every gRPC exception code. We've tested all of the HTTP exception codes. We've been able to trigger our myriad circuit breakers by raising circuit breaker exceptions to see what the application does based on that. We can delay applications. We've done this by inducing a timeout up to the timeout interval or just past the timeout interval. You know, if you have a timeout of 10, you might want to test the impact of a 9 and an 11. So we've done this programmatically to test all of these different failure scenarios, and they're all able to be tested using this annotation. So the last bit is writing those conditional assertions. So in that case where you want the system to basically, handle the error and return a pretty error message page, then you would modify the application accordingly. But chances are you'd want to write some sort of conditional assertion. And so here what we just say is we make the assumption for the simplicity of the talk that we want the system to return those gRPC exceptions. And so we update our test accordingly to specify that when no faults are injected, the fault injection Boolean should be assert false. When faults are injected, we get the actual error message that we want, which may involve remapping it if your application changes one type to another or whatnot. And then finally, we rethrow if none of these conditions are met, which is an assertion that's outside of what we talked about. OK, so the last bit, and this is kind of the last bit I'll do here to wrap up, is to talk about our standalone fault injection tool for doing testing and staging. Our standalone tool is provided as a CLI. It looks like this. It takes a functional test, which is any script that can indicate passing. If it returns 0, it indicates passing. This can be a Gradle file. This could be a Python test. We've seen some people have functional end-to-end tests that are simply curl statements that assert that some regex holds true on the website. That's fine. We can do that too, whatever you want, whatever works for you. And we also provide an HTTP API for performing those conditional assertions. If you need to say, like, for instance, my curl regex will do this when no faults are injected, otherwise it will do this. So we try to support whatever the developers want here. And what we imagine and what we are working on integrating today is kind of doing a staged approach where developers use an analysis configuration that tests for common errors in development to keep that really fast, where they can work locally and get used to testing for unavailabilities or errors. And then in a nightly build, for instance, we've done this in code build, we say, like, test everything, like test every possible thing for every possible error. And so this configuration allows you to integrate it to whatever level you want in your application. Finally, the last little bit that's nice is that it provides a counterexample that can be used to replay failures. You have a failure in staging, and that failure occurs, it will produce a file, and you can take that file from the staging environment, run it locally as long as you have the same version of the code, and attach your debugger, and you can examine, you can replay a failure that occurred in your staging environment locally in a way where it's just much nicer to debug. And similarly, this could be used if you want to use that counterexample file to kind of craft particular scenarios that modeled outages you saw in the past to serve as a regression test or similar. Okay? So just to wrap up here, most of my work today has been on microservices. Microservices are this interesting socio-technical problem because they go against the ways that we would normally kind of think about writing distributed systems. They enforce a style of programming that is used to support a social goal of organizational growth with rapid feature delivery. And so what ends up happening here is that it introduces a number of interesting fault tolerance challenges. We don't think about just error or success. We think about graceful degradation. We think about getting developers to think about how they can fail individual components and keep the system online. It's a new space. It's an interesting space. And the key here is that you need to start at the lowest level. You want to get your developers. Not everybody is going to be a distributed systems expert. Not everybody is going to have attended TLA Conf, for instance. Not everybody is going to have this knowledge. You're going to have developers who maybe aren't distributed systems experts or only have worked on distributed systems for a few months. And so the key is to mechanize thinking about failures early in the process to get them writing safer code and extend that and grow that throughout your organization. And the tool we talked about today, Filibuster, this provides a lot of that. This is towards the effort in providing that. And just to kind of close here, none of this would be possible without all of these people. Academic research does not happen in a small little self-contained bubble. There were a lot of students who worked very, very hard on building out all of the components and doing the required evaluations. So I just want to special thanks for all of those people. And that's it. Thank you very much. How have we been able to? No. So no, the problem is we haven't had it at a company yet, right? So we're working on, this is the problem of doing academic research is you can't really, so first of all, it's hard enough to quantify like, I fixed that bug and I knew that that was going to cause $1 million outage. That's really hard to do in general. It's very, very hard to do in a lab where you don't have access to anything real. So what we have been doing, I can tell you, is multiple things. So we're working with the company to deploy this in production so we can start doing that. And we'll start looking at bugs discovered and try to figure that out. In addition to that, we performed a qualitative study where we examined, I don't know, where it's an in-progress qualitative study, I'll say, where we've been examining a corpus of 1,000 postmortems. And those postmortems detail all of the root causes. And so most of the design decisions that we've been making in figuring out how to mechanize this and apply it towards real bugs have been made based on that. So I am the one. I'm only about 300, I think, through the 1,000 now. It's a grounded theory study. And I've learned quite a bit. And a lot of the decisions here are informed by actual bugs that we observed. So this is about as good as we can get other than having it completely integrated and working as part of somebody's daily workflow. Yeah, so it is all open source, except for one thing, the Java JUnit stuff. My big thing was I had a slide, I was going to reveal it today. It's all open source today. But I got a paper accepted and I have a camera ready due. So that open source announcement probably won't happen until Monday. But yeah, it's coming. It's just, I only have so many fingers and so many computers. Yes? Like trying to programmatically generate corpuses? Corpora? Yeah, I mean, there is some, it is possible to do that. Generating the graph. So there's been a ton of work on graph characterization in academia. There was one paper that looked at Alibaba and got traces. They said Alibaba, they've got 76,000 microservices. Here's a collection of 7 terabytes of traces. That's great. A trace doesn't tell me anything about what your application is doing. It's actually really hard to figure out what the application is doing from the trace alone, right? And there is some work. There's a paper by one of Peter Alvaro's students that just is at the same conference as mine coming out in about a month that says, can you figure out what applications do from traces and stuff like that? It is tremendously hard to do. And what I'll say here is that even with those data sets that are traces alone, it's not going to let me find the application bugs that cause problems, right? Like the application that has a circuit breaker that's misconfigured and doesn't close when the incident's resolved, like, sure, a trace will exhibit those characteristics, but when I'm searching through the traces, I won't know how to find that trace to pull out and play with that. So I think that any generation needs to take the application structure and the content of the application and the concurrency and internal implementation details into account for it to be successful for this kind of work. Yeah, I think that's it. But anybody has questions, I'll stay here. You can come and find me. But thank you very much. I appreciate it.